So in this chapter, we are going to talk about acids and bases, all the different kinds that there are. So in the acids bases, the first theory of acids bases was the Arrhenius theory, in which case the acids were proton donors, whereas the bases were hydroxide donors. The theory got revised later on, and then came the Bronsted-Lowry theory, which is that the Bronsted acids donate protons, H plus ions, and the Bronsted base accepts the protons, which is the H plus ion. Again, just a reminder, protons are synonyms for H plus because the hydrogen has only one electron and one proton, and since the electron has gone away, there is only a proton left, so really it's just a particle now. It's not an atom anymore. So that's what a proton is called. Here is an example of a very common acid-base reaction. And here is an acid, HA, and if you want in your mind, you can think about HCl. Here is a base, and what the base does, it takes a proton from the acid. The proton goes away, leaving its electrons on the A, which is the anion, because remember, the H plus is going to go away from the acid. So then you end up getting A minus and HB plus. Okay, so now the acid will give you the conjugate base. The base will gain the proton and becomes the conjugate acid. So in a typical acid-base reaction, this is what happens. These arrows over here, these can be equilibrium and these can be straight yield arrow depending on what kind of acid base you're dealing with. If it's a strong acid and a strong base, then it's a complete yield. There is no equilibrium. But if it's a weak acid, weak base with a strong acid, strong base, then it's going to be in equilibrium. So these are written right now in equilibrium, but do not pay so much attention to this right now. Focus more on the acid and the base. So again, acids are donating the protons, whereas bases are accepting the proton. Okay, acids will give the conjugate base, bases will give conjugate acid. So here are some examples with the true acid and base. So for example, here amide, NH2 minus is the base, the acid is the water. So NH2 minus picks up a proton from water. The proton leaves, and remember when the proton leaves, it's leaving its electrons behind right here on the oxygen. So now the NH2 minus has picked up a proton, so it becomes NH3, whereas the electrons that were left by the hydrogen are now on oxygen. So this HO is now the hydroxide. So because this acid has lost a proton, it gives you the conjugate base. The base, which has picked up a proton, now becomes a conjugate acid. Here is an example with an acid, typical acid, HCl, hydrochloric acid, and the base here is methanol. You can think of methanol as water also if you want to. You can ignore the CH3 and substitute that with H. If you want to, you'll still get the same kind of reaction. So here, the oxygen will pick up the proton over here. And this is actually what we call mechanism. This is the arrow pushing, this is the mechanism. This is showing exactly where the electrons are being transferred, what are the new bonds that are forming, what are the bonds that are breaking. So this is called electron pushing, and a mechanism of a reaction is what we follow a lot in organic chemistry. And so that's what this is. If you want to look at this without the arrows, just look at the fact that you have a base, which is CH3OH, which is picking up a proton and becoming a CH3OH2 because it's picked up a proton. Whereas the HCl, which lost the hydrogen, became Cl minus. Okay, the arrows just help to show how the new bonds are being formed. That's all, because the new bond is forming now between oxygen and hydrogen. So oxygen and hydrogen, that's formed a new bond. Also note the charges over here. Okay, so oxygen here picked up a proton, and because of that, it now has 3 bonds, which means now it will have a formal charge of +1. So you have to show that. This is called the oxonium ion, and so you have to show the plus sign there. Whereas in the acid case, when the hydrogen left and it left its electrons on chlorine, now it has excess electrons and it became a chloride ion. Remember, the acid will give the conjugate base, the base will give the conjugate acid. Okay, that's how we have an acid-base reaction. So on the left-hand side, you will have the acid base, and on the right-hand side, you will have the conjugate acids and bases. There is a rule for forming conjugate acids and bases, and that is when you have a strong acid, it ends up giving a weak conjugate base. And this is a very important fact for organic chemistry. This is possibly one of the most important fundamental topics in organic chemistry, understanding acids and bases. So if you did not understand that in Gen Chem, understand it now, because it's going to stay with you for Organic Chemistry 1 and Organic Chemistry 2. So a strong acid will give a weak conjugate base. A weak acid will give a strong conjugate base. A strong base will give a weak conjugate acid. A weak base will give a strong conjugate acid. Okay, and that's how it occurs. And this is the rule, this is how it happens. So here we have HCl. As in the previous reaction, HCl, which is hydrochloric acid, is a strong acid, so it ends up giving a weak base. Okay, so that's the conjugate base. Water, which is really quite a weak base, it's kind of amphoteric, it can be acidic or basic. And so water is a weak base, and in front of hydrochloric acid, this is the base. And so this is a weak base, and this weak base becomes comparatively a stronger acid now. Okay, and this is the conjugate acid here. In this case, where we have acetic acid and ammonia, acetic acid is an okay acid. Okay, it's not very, very strong. So it gives a nice strong conjugate base. Ammonia, which is a weak base, will give a strong conjugate acid. Remember, acids are always going to be more positive and bases are going to be the negatives. Okay, bases have more electrons in them. Okay, whereas the acids, they have protons in them. So whether you have acid on the left-hand side or on the right-hand side, the acids are always going to be positive, because they have that extra hydrogen in them. Okay, so HCl was the acid here, and hydronium ion is the acid over here. It's the conjugate acid. Same thing here. Acetic acid, which is a proton donor here, is now become the conjugate base, but ammonia now picked up the proton, so this became the conjugate acid, which has the extra proton. I just want to make a little note over here about the arrows. If you look at the arrows here, this arrow is a straight arrow, which tells you that you're reacting a strong acid and fairly strong base, not fairly strong base, but in front of the HCl, this is a good base. And in this case, this is an equilibrium arrow because both of these are weak. Okay, and so we use equilibrium arrow. Again, this is not such a big point, but just to make a note of it. Here are some examples of acids and bases. It's a good idea to keep this table handy so you have a good understanding of what these acids are. All acids and bases can be divided into two, organic and inorganic. Inorganic are very easy, as you have seen them before. Hydrochloric acid, sulfuric acid, water, nitric acid, phosphoric acid. Those are the inorganic. These are also called the mineral acids. Organic acids, the one that you are most familiar with, is the acetic acid, which is the common vinegar. Citric acid is the one that you drink all the time in the juices. For bases, the inorganic bases are pretty much all hydroxides. There are no hydroxides given here. Well, there's a hydroxide given here, but there's a counter ion. So whether it's sodium hydroxide, potassium hydroxide, calcium hydroxide, whatever it might be, all hydroxides are going to be bases. Ammonia is a good base. Ammonium hydroxide is a good base. Amides are bases. And then some carbonates and hydrogen carbonates are good bases. So for example, sodium carbonate, sodium hydrogen carbonate, those are considered to be good bases. Organic bases are varied. Okay, and so here is some amines, methoxides, and as we go on, we will learn more about these bases because organic bases are quite different than organic acids, and you may not have encountered them so much in general chemistry, so you will see them a lot more now, okay, than you did before. So here are some solved problems. Okay, so what is the conjugate acid of NH3? So without looking at the answer, you look at NH3, add a proton to it, and if you add a proton, you literally add H plus to that. And if you add H plus to it, you get NH4 plus. So here the question is, what is the conjugate base of HSO4 minus or hydrogen sulfate ion in the reaction below? So you look at the ions, and here's the reaction: carbonate plus HSO4 minus to give hydrogen carbonate ion and the sulfate. So the conjugate base of HSO4, meaning that you're taking the HSO4 and you're losing a hydrogen there. So this is the only conjugate base possible. Conjugate bases would have lost hydrogens. Conjugate acids would have gained H pluses. A strong acid leads to a weak conjugate base, not a strong one.